Okay, so this is part 2 of Unit 6, and we are going to finish talking about some aspects of acid-base equilibria. So in the last video, we started getting into predicting the pH and the K values for acid-base solutions, and now we're going to get into a little bit more about that in terms of the calculations, and then we're going to go from there into dealing with polyprotic acids and really talking about what makes something acidic or basic. 186 is where we left off. There we go. So we left off with this slide where we were talking about whether the K value for this reaction was going to be greater than or less than 1. And we kind of need to think in terms of these two acids that are here. So we have HCN in water, which is going to dissociate to give us H3O plus and CN negative. Now we know that the K value for this is 6.2 times 10 to the minus 10. It's highly reactant favored. It wants to stay on the left of this reaction. Then we have this guy, where we have technically F minus plus H3O plus going to HF and water. And we know this because HF dissociates to give F minus by donating a proton, and it's just the opposite here. So originally, if we were talking about it in this direction, in the forward direction where HF dissociates to give H plus and F minus, it would be 7.2 times 10 to the minus 4. By reversing this, we now have 1 over K, or 1 over 7.2 times 10 to the minus 4. And technically this is going to be a big number. It gives us something like 7.2 E negative 4. 1.4, we'll just go with 1.4 times 10 to the third. That's a large number. But when we talk about this guy and this guy, this is so small that this cannot compensate for that. And so we really have to look at, obviously this is going to be less than 1. Now if we wanted to actually solve this, what is the K value? I'm going to show how I would do it. It's very similar to Hess's law problems, where you take your two-step reactions and you try and line them up so that they are going to give you the overall target, which is this for us right now. So we know we have HCN in water that can dissociate to give H3O plus and CN minus. K value here is equal to H3O plus CN minus over HCN. There it is. Okay, so we are going to try and set it up in photon to get at the hydronium ion and F minus, giving us a K value where the concentrations are equal to hydronium times F minus times over the concentration of HF. Water is excluded. Now if you look, HF is technically over here. The K value for this guy is CN minus HF over HCN times F minus. So we want our two K values down here to be multiplied so that this is our total product. Now, CN is in fact on top. HCN is on the bottom. However, HF and F here are flipped. So we need to do 1 over K value. 1 over K here is going to give us HF over F minus and H3O+. At this point, we can take these two K values, KHCN which is H3O plus times Cn minus over HCN, and multiply that by 1 over the K value for HF, which is HF over F minus times H3O plus. Hydronium cancels and gives us our overall total. So to find the K value for this guy up here, we're going to take the K value for our HCN times 1 over the K value for HF, and that's going to give us 6.2 times 10 to the negative 10 times 1 over 7.2 times 10 to the minus 4, which gives us something like 8.6 times 10 to the minus 7, I believe. Yes. Whenever you're doing this, make sure you are considering, guys, following your math. Write out what you are looking at, write out what you are going to multiply. Simple mistakes like that can really cost you on a test. Whenever you have an acid-base problem, make sure you consider what reactions are possible, what is dominant, the left or the right, and really consider that, because that is going to give you the logic to really answer the question. And then if you have to, you can go into making an ice chart or eventually solving for your pH. So here we have an aqueous solution of HCl. HCl in water gives the hydronium ion and Cl minus. We also have water. Water always self-ionizes here to give H3O plus and OH minus. K value here is very, very high because it is a strong acid. K value here is very, very low because it's 1 times 10 to the minus 14. Now, if we consider this, there is some hydronium from water, but it's very, very low. Instead, the major species here come from this side of the equation, and then really this equation is dominated by the left. So our major species are H3O plus and Cl minus. And you can technically consider the fact that it is actually in water, but it's not going to contribute to pH, so we really don't care too much here. So to calculate our pH, we're going to take, we know that whatever we have here is going to completely ionize. So if we have 2.0 times 10 to the minus 3 molar here, 1 HCl is always going to give 1 H plus. Gives 2.0 times 10 to the minus 3 H plus. pH is just equal to negative log of that, which is 2.70. We could have considered this concentration from water, but really it would have been something like 2.7001 or so, and we just don't care enough to really go that far. pH of a 1.5 times 10 to the negative 11 molar HCl solution. Well, again, let's look here. HCl ionizes to H plus and Cl minus. Here we know we have 1.5 times 10 to the minus 11 molar. Water self-ionizes to give H3O plus and OH minus. Remember, guys, these two terms are really interchangeable. Here, this is 1 times 10 to the minus 7. Kw is equal to 1 times 10 to the minus 14. Square root of that gives H plus at 1 times 10 to the minus 7. So if we look, again, this is the major side of this reaction. This is the dominant side of this reaction. But technically, this water makes more of the hydronium than the acid does. And so if you did not consider this, if you just calculated the pH here, negative log, you would get something like a pH of 10.8. That is absolutely wrong, though, because you have to consider this. So our pH is really 7.0. It's a negative log of 1 times 10 to the minus 7. If we considered both terms, it's a negative log 1.0 times 10 to the minus 7 plus 1.5 times 10 to the minus 11, which is like 1.00015 to the negative 7. Nobody cares. Or I guess somebody out there might. But we can be confident that this is accurate enough to just say it's a pH of 7. Alright, so calculate the pH of a 1.5 times 10 to the minus 2 molar solution of HNO3, or nitric acid. Guys, at some point, pause this and really try to work it on your own. That's going to tell you whether you have enough practice to do well on the exam or not. If you've done that, we can now go ahead and work this out. In water, this is going to give us the hydronium and the nitrate ion. This is a strong acid, so it's a one-way acid. We know whatever we started with here is going to give us that concentration of our individual ions on this side. So to find the pH here, we're going to take the negative log of 1.5 times 10 to the minus 2. And you should get something like, So we consider both species. The acid here is definitely more concentrated than what the water would be. So we know that this side of the reaction is dominant here. Water is going to be dominant on the other. But because nitric acid is a strong acid, its conjugate base, that nitrate ion, is very weak. It does not want to go back to the molecular form. It wants to stay ionized. That means when we go to do this, we can consider not really having to worry about this water. Instead, water is only going to give a small portion of the H3O+. This is 1 times 10 to the minus 7, not something to the negative 2, which is, 10,000 times more concentrated. So we can really just factor in the fact that nitric acid is essentially the only contributor of the hydronium ion, and use that to find our pH. So when you are solving these equations, make sure you are looking at what is present. Consider what your sources of hydrogen or hydronium ions are, and write the equations. Consider your equilibrium constants, because you only have to consider the ones that are going to be dominant here, guys. And then write the expression for the overall expression. If you have to, you can make a ICE chart. And then if you have to, you can go further to either find your pH or other information. Guys, first and foremost, remember that chemists are lazy. If it's within 5%, and almost all of the problems I give you are going to be able to make that assumption where you can discount x at some point so you don't have to use your quadratic. As long as it's within a 5% error, we're pretty happy with that. So here, for example, we have a 0.8 molar solution of HCN. HCN in water is going to give us the hydronium ion and Cn-. We've already talked about this reaction a little bit. We know that this K is very small, so technically this is the side that is going to dominate. We know that the products aren't dominant because our K value is so little. Now, we can consider the equilibrium of water, the self-ionization that water has, but if you look, this K value is times 10 to the negative 10. This one is times 10 to the minus 14. Which one is going to control pH? Well, hopefully you can see that this one is about 10,000 times or 1,000 times, 10,000 times stronger. It's going to be more productive on this side. And so it's going to be our major contributor. And since it's our major contributor of H3O+, it's also our major reaction that controls the pH. Interesting. There we go. So calculate the pH of a 0.5 molar aqueous solution of HF. Same thing as before. We know that HF in water is going to ionize as H3O+ and F-. We also know that we have 0.5 molar initially. We know that technically water itself can self-ionize to make hydronium and hydroxide. The thing here, though, guys, is technically this is, I'm just going to say a tenfold factor less important in controlling our pH. So we don't really have to worry about this. We need to worry instead about this reaction here. That is going to be the one that contributes the most hydrogen ion. So if we look, we have some change where some of it's going to ionize, plus X plus X. This is 0.5 minus X, X, and X. Because this 0.5 is so much bigger than 7.2 times 10 to the minus 4, we can say that 0.5 minus X is essentially 0.5. And now we can go ahead and plug this in and say that our K is 7.2 times 10 to the minus 4. That is a 4. Which is equal to X times X over 0.5. It's going to give us 3.6 times 10 to the minus 4 times X squared. Square root of both sides. Should give us something like 1.9 to the negative 2. There we go. Okay, so that's going to give us, overall our information. So make sure you are setting this up to really go through the process here. Don't skip any steps. Okay. Now, we've talked a little bit about acids. We need to talk a little bit now about bases. We said that Bronston-Lowry says that that acids are proton donors. Bases are going to be proton acceptors. They're going to accept an H+ or a proton from the hydronium ion in solution. Now, they're going to have pHs that are greater than 7. And generally, our ionic compounds containing an OH with a group 1 metal are our strong bases. We can calculate POH the same way we calculated pH, negative log of the hydroxide. And we still have this relationship where pH plus POH is going to be equal to 14. So here we have sodium hydroxide. Sodium hydroxide completely ionizes into sodium and hydroxide. If we had a solution we wanted to calculate the pH of, we can do that. We know that this is a strong base, so it completely ionizes. So whatever we start with, 1.0 times 10 to the minus 3 molar NaOH. There's a 1-to-1 ratio of NaOH to 1 sodium. Oh, we're looking for hydroxide, I'm sorry. To 1 hydroxide. So it's 1.0 times 10 to the minus 3 molar OH minus. Now to go from this to POH is relatively easy. We could also do, honestly guys, the hardest thing about this is you could have more than one process. You can take this and go from hydroxide, use your Kw to find your hydrogen, or you can just find your POH and then go to your pH. I'm going to do it that way. So this is negative log of our hydroxide, which is 1 times 10 to the minus 3, which gives us a POH of 3. 14 minus 3 gives us our pH, which is going to be 11. Do the same thing for calcium hydroxide. I'd prefer it if you would pause and try this on your own, and then we can do it together. Calcium hydroxide will actually ionize to give a calcium 2+ and 2 hydroxide ions. This is a 1.0 times 10 to the minus 3 molar solution. We know every time we have 1 calcium hydroxide, we have 2 hydroxides. That means we have 2.0 times 10 to the minus 3 molar OH negative. Now, because of this fact, when you go to calculate the POH, you need to factor in that 2-to-1 ratio. And so to find our POH, it's going to be the negative log of 2.0 times 10 to the negative 3. Which should give you something like 2.7. pH plus POH is equal to 14. So 14 minus 2.7 gives you a pH of 11.3. Oops. If you're talking about bases, for acids they use Ka, for bases they use Kb. There's no difference, guys. It's still going to be the equilibrium expression. It's just that now we're talking about a base instead of an acid. pH calculations for bases are going to be basically essentially the same as that for acids. You're going to use the same formulas. It's just that you can have a slightly different approach. You're going to find POH usually first and then go to pH. Calculate the solution of a 2 molar ammonia. Calculate the pH of a 2 molar ammonia solution. Ammonia and water is going to give us the ammonium ion and the hydroxide ion. We could write the equilibrium expression for water, but if you look at this K, instead of -5, water is to the -14. It's not going to contribute as much hydroxide as ammonia does, so I'm not going to worry about water here. Now, we know that the equilibrium expression for this is ammonium times hydroxide over ammonia. We have 2 molar here, initially, 0 and 0. Our change is going to be minus x plus x plus x. So it's going to be 2 minus x, and x. 2 is definitely larger than 1.8 times 10 to the minus 5. So 2 minus x is basically 2. So we can plug this in. So we have 1.8 times 10 to the minus 5 is equal to x times x over 2. Gives us 3.6 times 10 to the minus 5 is equal to x squared. Square root of both sides. Is something like, our x value is going to be 6 times 10 to the minus 3. Okay? Now this is our hydroxide ion concentration. We can go from hydroxide to POH, which is a negative log of that 6.0 times 10 to the minus 3. That's going to give us 2.22, which gives us a pH of 14 minus 2.22, or 11.78. Make sure you are going through the process here, guys. Don't let it get too far ahead of you.